All right, so this will be the first lecture on cosmology by Daniel Baumann, and well, I would like to say that we're very lucky to have Daniel here. I mean, I think at the moment he may actually be one of the most highly cited cosmologists in the field in his generation. So Daniel did his PhD in Princeton University, then I think only 1 or 2 years in Harvard for a postdoc, went back to Princeton for a postdoc. Then became, I think, faculty in Cambridge University. Now he moved to combined 50-50 Taiwan University of Amsterdam. Daniel is not only famous for all his research papers, but he wrote one of the most famous lecture notes on a graduate level on inflation, which is very relevant for cosmology, but also recently finished a book really teaching cosmology at a more undergrad level. So I think, he's kind of the perfect person here to explain you all in 3 lectures on cosmology, and thanks for coming.
Okay, thank you very much. Thanks a lot for the invitation. It's really a pleasure to be back at CERN. So I gave these lectures 2 years ago. It was a lot of fun, but it was online. So it's really fantastic to see everybody here in person. And so hopefully also we can make it interactive. You can ask me questions. You shouldn't have to wait until the end. Just stop me at any time if you want to interject with questions. Okay. As Wilke said, so my task is to teach you all of cosmology in like 3 hours. It's pretty much impossible. It's a huge field, with many different aspects. So what I will try to do is instead just give you a really broad picture of kind of some of the most important elements of the structure, history, and the components of the universe. And I will have to suppress technical details, although today we will do a very tiny calculation, okay, just in this lecture. Otherwise, there will be not very much equations and math, okay? If you're interested in more details, there's a very good book at roughly the same level as this course, which is by Barbara Ryden. It's a book of cosmology for undergrads. At a higher level of master's students, okay, there's also a book that I wrote recently. So we have 3 lectures. Roughly speaking, I will be dividing this into these 3 parts. So today we're going to be talking about the expanding universe. We're going to try to derive the equation for the expanding universe, discuss a little bit the structure of the hot Big Bang. And then tomorrow we will start talking not just about the homogeneous universe and its evolution, but also what happens to the evolution of small fluctuations in the universe. So as we will see, there were small density fluctuations imprinted in the initial conditions of the hot Big Bang, and I will describe how those fluctuations grow in time to form all the structures that we see around us. And then finally, in the very last lecture, we're going to go even further back in time and try to explain where these initial conditions potentially came from. Okay? That last part is going to be the most speculative. Everything before that is just an absolute fact that I'm going to be telling you, and then the last lecture will have some speculative elements in it. Okay. So let me start with today's lecture about the expanding universe. So the goal is going to be to derive and then ultimately also solve the equation describing the entire universe. Okay. Sounds like a huge task because we have trouble, predicting the weather, next week here on Earth. However, fortunately, kind of when it comes to the universe, as we go to very large scales and average over all the complications that we have on short distances, and also when we go back in time where things become more and more smooth, the description of the universe, as we will see, is exceedingly simple. Okay? In fact, it's going to be described by one single function in time, and we're going to be able to derive this function differential equation that this function will satisfy. So the mathematics of the universe is much simpler than the microscopic physics that governs it. So the story starts, roughly speaking, at an observational level in 1929 when Hubble discovered this velocity-distance relationship between galaxies. So what you're seeing in this plot here is actually Hubble's original data here, which is plotting the velocity of individual galaxies versus their distance. Okay? And so the distance is measured in funny units called megaparsec. A parsec is 3.26 light years, and then mega is 10 to the 6 times that. Okay? It's a funny unit that we can discuss later. Why? Because astronomers like to measure distances in that way. And then the velocity here on the y-axis is measured in kilometers per second. Okay? And so you see here, actually Hubble at the time didn't have all that many measurements. He took redshift measurements from Sliver, I think he's called, somebody else in fact. was giving him the measurements on the y-axis, and then he was using a specific technique using Cepheid variable stars to measure the apparent luminosities of these galaxies and then compare them. He was measuring apparent luminosities. The Cepheid variable stars was giving him a measurement of the absolute luminosities, and by comparing these two things, he could infer distances. Okay. In fact, measuring distances in cosmology and astronomy is the most tricky part of anything. Measuring velocities from redshifts is very easy, but measuring distances is not so easy, and is still being debated today. Okay, but when you do this, as you can roughly see here on the left, you get some correlation, meaning that galaxies with higher velocities are also further away. Okay? It's not extremely convincing on the left, but then there was further data that he was taking in 1932 together with his assistant. These red data points going out to further distances and larger redshifts. And there you can see more clearly that there's this roughly linear relationship between the velocity of a galaxy and its distance. Okay? And so therefore he then proposed this velocity versus distance relationship called the Hubble law. Okay? And there's a constant parameter called the Hubble constant that relates these two, which is just giving you the slope of these curves. Okay? So now in general relativity, we interpret this Hubble law as an effect coming from the expansion of space. Okay? So imagine you take at a given moment in time the distance between 2 points in space, like 2 galaxies, and here I've drawn a triangle, so you can take any 2 galaxies seen on the sky at a given moment in time. You wait for a certain amount of time, this triangle will become bigger, so the distances between all points will become larger. Okay? And so if the initial separation here is called R0, at some later moment in time, the distance will increase, and it will increase by something called the scale factor, A of t. Okay? And the scale factor is kind of, and it's, since the universe is homogeneous and isotropic, the same in all directions and the same at all points, any 2 points will just increase by the same amount. Okay, and it's separation between any 2 points, and it's all described by a single function of just time, not space. There's no dependence on location in the universe. It's just a single function of time called the scale factor. So now if you take this relationship here between initial distance, final distance, and the scale factor, taking a time derivative will give you the velocity of the galaxy. Okay, and then factoring out the scale factor actually gives you the. Sorry, I'm not figuring out how this works. But so taking the time derivative, which is indicated by this over dot of distance, can also be written as a time derivative of the scale factor divided by the scale factor times the total separation. Yeah? Because this total separation here includes the scale factor, it just cancels out here. And so then you can identify the Hubble parameter as this ratio of A dot over A. Okay? So let's keep this in mind, because we're actually going to be deriving now a differential equation for this Hubble parameter H, or the ratio of A dot over A. Okay? Any questions so far? No? Okay, so now if you go to the data and actually measure the slope, the slope of nearby galaxies, you can infer the Hubble constant, the value of this Hubble parameter today. So this tells us how fast the universe is expanding today. It has a value of 68 plus or minus 2 in a little bit of funny units, where it's measured in units of kilometers per second per megaparsec. And that's just because we were plotting velocity in kilometers per second on the y-axis, distance in megaparsecs on the x-axis, so the slope will have those units. But of course, megaparsec is a measure of distance. It's 3.2 times 10 to the 6 light years, and light years you could convert into kilometers if you wanted. And velocity has distance in it as well. So actually you could cancel kilometers against megaparsecs, and you would get units of 1 over time, 1 over seconds, or frequency. Okay? This means if I take an inverse of this Hubble constant, I will get a time scale. Okay, so let's just do that. Take the inverse of this Hubble parameter. You get a time scale from this measurement here, which is about 14 gigayears. Okay? 14 billion years. And so that's very roughly the age of our universe. Okay? So in detail, we will have to take into account that the universe, is slowing down initially because there's matter in the universe, and later on it's actually going to accelerate again because of dark energy, and that will change this number ever so slightly. But it will change it by an order 1 factor. Okay, so very roughly speaking, this dimension and kind of the scale that we're inferring by just measuring the expansion rate today is telling us roughly the age of the universe. Okay? And the precise age of the universe is 13.8 billion years when you take these complications into account, but we're getting it roughly correct by just this rough measure. Yes? Maybe use your...
Okay, this is probably like a slightly not that important of a question, but is dh more like the radius or like the diameter?
I'm going to come to d in a moment. So far I've only talked about th. Yeah? So I've talked about the time scale, the characteristic time scale of expansion. And basically, if you ignore gravity and just have expansion today and you trace it back in time, this is the moment in time where without gravity, everything would be sitting on top of each other. So that gives us a rough measure of the age of the universe. If I now multiply this by the speed of light, I get a rough measure for the size of the universe. Okay? And so that's what I'm kind of showing you here. And you see that it's big, 10 to the 26 meters. The universe is a huge place. Okay? And so you instantly infer this just from the kind of the speed of light times the time scale. This is how far light travels very roughly. Again, in GR, we'll have to take into account the effect of gravity a bit more carefully. But very roughly, if the universe has an age of 14 gigayears, and light travels at the speed of light, it will cover that amount of distance. And so that's the observable size of the universe. Okay? Sorry. All right. Any questions so far? Now we're going to do a little bit of math. All right. So I actually want to derive for you one of the most important equations in cosmology and just show you that there's nothing, that you can do it. Okay? But I will also show you when we get to that equation. And so if you're not a fan of math, then you can also, for the next 5 minutes, kind of view this as art. And then when we get to that equation, we can continue from there. Okay? But actually, this equation is remarkably simple to derive, even just using Newtonian gravity. Okay? Of course, the expansion of the universe really is an effect of general relativity, so it's a little bit, it hurts my stomach a little bit to do this in Newtonian physics, because in Newtonian physics, space is not dynamical, and so it's a little bit funny to do this, but it's the best way we can do now if you want to do this equation quickly. Okay? So let's imagine we have a spherical region in space, and the universe is homogeneous, so we can put this region of space anywhere we like. Okay? And let's look at a test mass, this little mass m, at a distance r from some arbitrarily chosen position in space. Okay? And since the universe is expanding, this distance of the test mass will change in time, and we would like to have an equation of how this equation changes in time. We'd like to know its velocity and acceleration as a function of, for example, the density of the universe. So the way we derive this in Newtonian gravity is simple. We just ask, first of all, what's the force on the test particle on the surface of this sphere? And the force is just given by Newtonian gravity, so it's just this 1 over r squared force. Okay. And then we use F equals ma to relate the force to its acceleration. Okay? So little m has cancelled because the force, of course, depends on capital M, which is this. Capital M is the mass inside that spherical shell. There's actually no force coming from anything outside of the spherical shell. In GR, this goes by the name of Birkhoff's theorem, but in Newtonian gravity, you can also argue for this to be true. So the force is only coming from the interior mass. So that mass I'm calling capital M. Little m, remember, was the mass of the test particle, but that appears on both sides. It appears both in the gravitational force law and it appears in ma. So then we have an equation that just describes the acceleration of this test mass under the force generated by this total mass, capital M, inside of that spherical region. And so then a useful trick is to multiply this equation by the velocity, dr dt on both sides. Multiply by dr dt. And then you can integrate both sides, because dr dt times acceleration is just 1/2 dr dt squared. Okay? So it just gives you the velocity, the kinetic energy, basically, per unit mass of the particle. While integrating the other side with a dr dt added as a factor, gives you just the gravitational potential per unit mass of that test particle. And so the sum of the two is just a constant. Okay? So this just is called the first integral of motion in classical dynamics. When you have an equation of motion from the force law, you can integrate it once. That gives you a constant, just the constant energy of the system. So this test particle has energy conservation built in, where there's a kinetic energy per unit mass and a gravitational potential energy per unit mass, and the two are added together, and they're always constant. Is that clear? That's really the only non-trivial math we were doing in this derivation. Okay? And so then the next step is to substitute the mass of this interior region in terms of its mass density. So density times, here you see this is the volume of this spherical region, 4 pi over 3 r cubed. Multiplying volume times mass density gives you mass. So I can substitute this capital M here in terms of a density. And I can also substitute for r of t this relationship between scale factor and some constant reference distance that I'm choosing at any given moment in time. When I do this, this equation, this first integral of motion, translates into an equation for the scale factor. And you precisely discover this ratio of a dot over a, namely the Hubble parameter that we had in the Hubble law, on the left-hand side. Okay? You get density on the right-hand side, maybe by moving this thing here to the right-hand side, and you have this constant of integration that appeared as a third term. Okay? So this is a famous equation called the Friedmann equation. It's kind of the 0th law of cosmology. Everything about the expansion of the universe follows from this equation. Okay? So are there any questions on this mini derivation? Otherwise, the slides are online. You can do it in your own time and make sure that I didn't cheat. Yeah? Right? Okay, so this is a very important equation, and we want to analyze it a little bit further now. Okay, we're going to just be now using, try to find solutions to this equation. Okay? But first of all, let me explain a little bit more. In particular, let me explain the meaning of this integration constant, this extra third term that appeared here. So as you can see, this integration constant can be positive, negative, and 0. So there are actually 3 different cases and 3 different types of model universes that can appear, depending on whether this constant u is positive, negative, or 0. So if it's positive, then it means that everything on the right-hand side is positive. And so therefore, a dot over a squared can never become 0. So the universe will never stop expanding. Okay, so it will expand forever, because the right-hand side has a constant, and so then the square velocity on the left-hand side will never go to 0. If u is negative, though, then the first term here typically is positive because densities are positive. The second term now can be negative, and you can get a balancing between those 2 terms. So for some moment in time when the density has decreased enough, these 2 terms can exactly cancel each other and become 0. So what happens then? The velocity becomes 0, and the universe stops expanding, and then it will turn around and collapse again. So this would be the case where the universe expands, it stops at exactly some critical moment when these 2 terms on the right-hand side cancel each other, and then it recollapses. Because the density keeps dropping down, and so then if there's some moment in time where the density is just low enough to have this cancellation, the next moment in time the density will be smaller, and the left-hand side becomes negative, and this means the universe is collapsing rather than expanding. Okay? And then finally, there's kind of the limiting case where u is exactly 0, and that means the universe expands, but asymptotically it stops expanding. Asymptotically meaning in the infinite future. That's exactly the limiting case where it doesn't expand. Well, whether it expands forever or not is a bit of semantics. It expands forever, but stops asymptotically in the infinite future. Okay? It's exactly the limiting case between those 2 extremes. So now, and then in GR, it turns out you can map these things to the curvature of space, of the spatial slices that describe the universe. So the first case where the universe expands forever is negatively curved on 3-dimensional slices. The second case is positively curved, and the last case is spatially flat. So these spatial slices satisfy the axioms of Euclidean geometry. The other 2 don't. And it so happens that observations seem to favor this very simplest case, where the universe has exactly spatially flat slices. Okay? And parallel lines don't meet, and the triangles have angles that add up to 180 degrees. Yes?
My question was, how confident are we that it's flat? Like, what's the degree of error?
At the percent level. So there's something that you can actually measure kind of these parameters in this equation, and the last term can be expressed in a so-called curvature parameter, and that curvature parameter is known to be 0 at the level of a percent. Yeah. Many other parameters in cosmology actually we know much better than 1%. So this curvature parameter is one of the least well-measured parameters, although it's very well measured by the standards of astronomy. But cosmology standards have risen so high that it's actually one of the worst measured parameters in the cosmological standard model, I would say. Okay, so now for now, therefore, we will ignore the curvature of spatial slices. We will ignore this integration constant and always just work with the simplified Friedmann equation, where the expansion rate of the universe is just determined by the density rho. Okay? So if you measure locally the density, or over some average volume of space, the density of the universe, you predict how fast space will respond to this density. Okay? But before we do that, actually, we can just like do the measurement itself, because we know what the Hubble parameter today is, the Hubble constant. We have measured it. So you can then determine what the average density today is, just from that measurement. And here I've shown you the measured value of the average density today in different units. And maybe the most intuitive one is the one that there's 5 protons per cubic meter, because we can draw a cubic meter in space in front of us. And if you spread all the matter in the universe uniformly, you would have 5 protons in some cubic volume of space. Yeah. There's other measurements like 10 to the 11 solar masses per cubic megaparsec. Okay. This is roughly the number of, a solar mass, of course, is roughly an average mass of a star, and 10 to the 10 is the rough number of stars in a galaxy. So this tells you that's like 1 galaxy on average per cubic volume with a side length of a megaparsec. Okay? And so the average separation between galaxies is also a megaparsec. And that's one of the reasons why cosmologists like to use this unit of megaparsec, because it's the average distance between galaxies. Sorry, I keep going. Hold on. Okay. All right. So now I was deriving this equation in Newtonian gravity. I told you it's a little bit of a fake, but you can do this properly using the Einstein equations, and here they are. Okay. The Einstein equation, when you apply them to a homogeneous and isotropic universe, will precisely give you this Friedmann equation, except for one small technical aspect, that what the Einstein equation actually gives you is the energy density, not the mass density of space. Yeah? And so this means also that when derived in GR, rho should really be interpreted as an energy density, not as a mass density. And so therefore you can apply it to relativistic particles. This Newtonian derivation that I gave you actually, strictly speaking, only applies to non-relativistic matter. But when you upgrade it using relativity, you can also apply this same equation to relativistic matter like photons and neutrinos, if you interpret this density rho in terms of an energy density. But for now, I will just use these two concepts interchangeably. So we can always now, from now on, just let's think of rho as an energy density rather than a mass density. Okay? Okay. So now, of course, if we want to solve this equation, we can't yet solve it because we don't know how the density evolves in time. So it's not yet a closed system of equation. We have a first-order differential equation, but the right-hand side depends on the parameter rho and not on the scale factor. So if we could figure out what the scaling of this density with the scale factor is, so how does the density change as the universe expands, then we had a closed system of equations and we could solve this equation. Okay. So to do this, we have to first of all ask ourselves, what are the different components of the universe? Because different components will evolve, their density will evolve differently. So the density of matter evolves in a certain way, the density of radiation evolves in a certain way, dark energy, they all evolve differently, and so we need to split things into their components. And so it turns out that the universe is filled with 4 different types of components, energies. So there's ordinary atoms, of course, that you and me are made of. That makes up only 4% of the total energy budget of the universe. The majority of matter is pressureless dark matter, as you just heard from Bradley. And then a small sliver today is radiation in the form of photons and neutrinos. But actually that radiation turns out to be the most dominant contribution when you go back in time, because things evolve differently when you go back in time. And then the most mysterious, but also the largest component is this dark energy component that we will also discuss. Okay? So now we need to determine how each of these components evolve, how their density depends on the size of the universe, to use this then as a source in the Friedmann equation. Okay? So what we will do is, let's just imagine we have a fluid in a box. And again, the universe is homogeneous. We can put this box anywhere. We just choose it large enough so that the universe can be treated as homogeneous. And this box can be filled with matter particles and radiation. But on a coarse-grained sense, we describe it by a volume, an energy, total energy inside the box, and the pressure. Yeah? So for a fluid, that's enough. The fluid is described by energy, pressure, and volume. And then the energy density is just the ratio of the total energy in the box divided by the total volume in the box. And so now we would like to know how this evolves when we change the volume of the box. Okay? So of course, you probably all know the real way of deriving this would be to appeal to the first law of thermodynamics. Okay? It gives you a relationship between changes in energy to changes in volume and pressure and even heat flow, but there can't be a heat flow in a homogeneous universe, so that term is 0. So in an appendix, I actually do that derivation, but I decided to cut it out because I've shown you enough math already. Okay? So there will be an appendix to these slides where you do this derivation. But the results that we get from that derivation are very intuitive, so we might as well just guess them. Yeah? So I'm just going to show you the final answer for how the density evolves with the scale factor, and I'm hoping that they will just be so intuitive that they hardly need the derivation. But if it's not intuitive enough, you can go and see them derived. Okay? So let's start, for example, with pressureless matter. So pressureless matter, imagine just a set of particles that move at slow speed, so they're non-relativistic, and we increase the size of the box. The energy of each individual particle is dominated by their rest energy because they're moving slowly. And so therefore, that energy doesn't change as I'm changing the volume. Makes sense, no? So E is constant as I'm making the volume bigger. But as I make the volume bigger, the volume increases by 3 powers of the scale factor. Okay? And so therefore, the ratio of E over V will scale as the inverse of 3 powers of the scale factor, just by the fact that energy inside of the box stayed constant and the volume increased each side length by 1 power of the scale factor. In 3 dimensions, it's 1 over the scale factor cubed. Okay? So you can derive this from thermodynamics, but I think it's totally intuitive that for non-relativistic matter, the energy inside the box doesn't change and the volume gets bigger. And that's the only effect that's happening here. Okay? So then you can take this scaling of rho proportional to a to the minus 3, feed it into the Friedmann equation, and now it's a closed equation because the right-hand side depends on a, the left-hand side depends on the time derivative of a, and I can just integrate that to get a proportionality between the function of the scale factor as a function of time. And if you do this with there's a factor of 2 here and a 3 here that converts into a 2 and a 3 here when you do this integration. And so you get a famous t to the 2/3 scaling of a matter-dominated universe. So if the universe was filled with only matter, the scale factor goes as t to the 2/3. Yeah? In my book, this will take you 2 chapters to get there, but we got there in like half an hour. Okay. All right. So now the second case is the case where we're studying relativistic matter, so like massless particles. And now when you make this box larger, there's a second effect that the wavelength of each of these particles also stretches, or their frequency goes down. And in quantum mechanics, you know that energy of a quantum is proportional to its frequency, or inversely proportional to the wavelength. So the energy of each individual photon inside of this box will decrease by 1 power of the scale factor. Make sense? Yeah? So now we can't take the energy to be constant, but instead there's an extra scaling of 1 over the scale factor, a decrease in energy. The volume, again, still goes up by 3 powers of the scale factor. That's what volumes do for a living. Okay? So now when you take a ratio of E over V, you get a scaling of a to the minus 4 rather than a to the minus 3. There was 1 extra power of decreasing energy. Okay? So now if you feed that into the Friedmann equation, you get a new scaling, which is that the universe evolves as t to the 1/2. Okay? And that's the famous scaling of a universe that's dominated by radiation. Okay? So now when you take those 2 scalings, we have measured these things today. I told you in our pie chart, I showed you that most of the mass of the universe, that the mass of the universe was a factor actually of 10 to the 4 times larger today than the amount of radiation. So today the universe is dominated actually by dark energy, but we will get to it. But there's more matter than radiation by a factor of 10 to the 4. But if I go back in time, these scalings of a to the minus 3 and a to the minus 4, the scale factor gets smaller when I go back in time. And so the radiation will increase faster. And so here I've shown you this on a log-log plot where these are straight lines, but with different slope. So one of those lines has slope minus 3, the other one has slope minus 4. And so, of course, at some point they will have to cross. Okay? And so that moment of crossing is called the point of matter-radiation equality, because the 2 densities are the same at that moment. And if you go even further back in time, radiation will dominate. Okay? So there's 2 eras now in this kind of simple picture where we just have radiation and matter. Initially, the universe is the hot Big Bang with just radiation and subdominant amount of matter. But then as the universe dilutes, radiation will dilute faster. At some point, this crosses. the universe becomes matter-dominated, and then ever since it was matter-dominated until the moment when dark energy reared its head. Okay? All right? Okay, so dark energy. So this was all kind of made perfect sense. It's consistent with the standard model of particle physics that there are these two components and they evolve in this way. So it was somewhat of a surprise to people that there was something else which was discovered in 98. And the way this was discovered is by noticing that the universe actually is accelerating today rather than slowing down. If the universe was only filled with matter and radiation, then gravity is an attractive force and it will try to slow down the expansion of the universe. So that was the expectation. They were expecting, if you measure the expansion of the universe today compared to the expansion of the universe in the past, the expansion should have been larger in the past than it was today. And if you go far enough into the past, that's indeed the case. The universe is expanding rapidly at early times, it then slows down. Okay? But then they discovered there was a transition point where the universe actually started speeding up again. Okay? And so that's this discovery of dark energy. This is the most current plot, or most current as of maybe 2 years ago, of measurements of supernova explosions that tell us the distance to very distant galaxies and the redshift. It's now plotted, unfortunately, in the opposite way. So there's redshift or velocity on the x-axis and distance on the y-axis. That's just the way I had it available. It's exactly the same Hubble diagram, except x and y-axis flipped. Okay? It's not a straight line because we're going to such large distances that the simple approximation of linear relationship between distance and velocity actually breaks down in GR. If it didn't break down, at some point you would be expanding faster than the speed of light. The galaxies would be faster than the speed of light. So in GR, there's a correction to this. And so this linear Hubble law actually turns over and becomes curved. And you're really seeing, we're going to such large redshifts that we're seeing this effect take place. But you can predict it. And so what you predict without dark energy is this dashed line, while what you predict with dark energy is this solid line. Okay? And so very clearly by eye, there's so many and so high quality data points now. Actually, compare this to Hubble. Hubble had 30 points. We could count them. Yeah? Here, actually, I have even problem plotting them. You have to plot them with opacity. And there's so many data points that when you plot them, in black and white, for example, it just looks like a blob of, thousands of measurements. So really things have completely transformed. Okay? But you can literally see by eye that a universe without dark energy is not consistent with the data. Okay? And you can see it even better here in this lower plot, where I'm plotting residuals rather than the complete distances. Residuals means I'm kind of dividing out by the best fit model. And you can see clearly here that the best fit model is this solid line, and the dashed line deviates from all of the data points by a significant amount. Okay? Okay. Any question? Yeah.
If we predict that the universe will at some point expand at a constant rate, like the asymptotic,
yes.
Does that mean that the amount of dark energy in the universe will be less than it is now?
Actually, I think on the next plot on the next slide there will be a plot that will answer this. Let me defer this to the next slide. Okay. Just before we get there, actually, let me just. So this source of acceleration, to be fair, is unknown, and we just at this point just gave it a name that that describes our ignorance. We call it dark energy because we don't know what it is. There's one good candidate for dark energy, which is just the good old cosmological constant that Einstein introduced. He introduced it actually because he wanted to have a static universe, and GR was predicting the universe to be expanding or contracting, and he didn't like this, so he wanted to balance this. So he added this extra term to his equations. Okay? This extra term can also be moved to the right-hand side, then it becomes a contribution to the stress energy tensor or the energy density of the universe. And when you do that, actually it turns out that it predicts a constant density. So the ratio of energy in a box of dark energy to the volume of the box stays constant when I make the box larger. That's, of course, exceedingly weird. Because what does it mean? It means that when I make the box larger, in order to keep the density constant, the energy has to scale as the volume. So as I make it bigger, there has to be energy being created at a rate that's proportional to the size of the volume. Okay? A good candidate, of course, is if that energy somehow is associated with space itself, because as I'm making this larger, I'm creating more space, and if there's an energy associated to space itself, then it's natural that it scales with the volume, okay? Okay? Now, if you take this constant energy density and feed that into the Friedmann equation, you get a constant expansion rate. So this ratio of A dot over A squared is now just a constant. And integrating that first order differential equation would give you an exponential expansion. Okay? So it's a differential equation that would then predict that the universe expands exponentially with a rate that's given by the expansion rate today. All right? And so this is the plot that I hope will answer your question. So if we now include dark energy as a constant energy density into this graph, previously we had a graph of two decaying energy densities for radiation and matter. Dark energy has a constant energy density. It's highly subdominant. Look, this is a logarithmic plot. So it's down by 30s order, many orders of magnitude at the time of BBN, for example, when the first nuclei were formed. It's totally irrelevant also when the cosmic microwave background were formed. But then just recently, at a redshift of somewhere between 1 and 2, I forgot the precise number, literally just yesterday in cosmological terms, dark energy was taking over because it doesn't decay. Everything else decays. So at some moment they have to cross. And it's a puzzle why it crossed just at this moment that we are alive, or in cosmic terms. I mean, if you look at this logarithmic plot, the crossover is here. We're living at scale factor 1, so we're living on this vertical solid line. There's this dashed line that I added that shows you when dark energy took over. There's a coincidence problem that, there's no reason why this should happen now. These energy densities presumably are determined by different types of physics. Why does that physics conspire to be of roughly the same order today? Okay? So I'm not entirely sure I understood your questions, but if you look at the asymptotic future would mean that matter and radiation become more and more suppressed, but cosmological constant stays constant. Okay, so I wouldn't say the cosmological constant gets smaller in the asymptotic future; it just stays the same. But the universe is bigger, and so yeah.
I'm not sure if you maybe already answered this, but do we have like an idea of the distribution, spatially, of dark energy as we do for dark matter? Well, there's a question: do we have observational evidence? Yeah, or so at a theoretical level, we really think if it's a cosmological constant, then it's really constant throughout space. At the observational level, it's a good question, in fact, to what degree we can put constraints on dark energy being clustered. Yeah. In some sense, it's a matter of definition, because once something that clustered is dark matter, and something that doesn't cluster is dark energy. So I think if dark energy really was strongly clustered, we should call it something else. At some point, we would then just call it dark matter or something. So, but it's a good question. Actually, I should think about it, whether there's ways observationally to really tell. The problem is that we have measurements of dark energy only on the very largest scales. So we just measure it from the very largest scale. So we don't have local measurements of dark energy just because its density is so low. So you can't measure dark energy in a lab here, for example, or with solar system tests of gravity and so on. The dark energy is totally, it's uniformly distributed. I told you that the average density today is 5 protons per cubic meter. That's the density mostly of dark energy, 5 protons per cubic meter. And so in a tabletop experiment to measure kind of 5 protons per cubic meter of dark energy is just not feasible, I believe. Yeah. Okay. So let me maybe skip the cosmological constant problem. You've heard about it before, probably. If you really interpret dark energy as this vacuum energy, then there's actually a way of estimating its size, and that estimate is just widely wrong. Okay. If you use standard quantum field theory, where matter fields will fluctuate. Those fluctuations have some kind of zero-point energy. Adding up those zero-point energies up to some shortest distance scale, some cutoff scale, gives you something, depending on what you choose for that cutoff scale, something that's orders of magnitude larger than the observed dark energy. So there's a problem why now, and there's a related problem of why so small and not much bigger. It's not a problem, it's easy to predict this vacuum energy, but when you do predict it, you predict it to be widely larger than what we observe. Okay, any questions about this part? Yeah.
So from everything that we have seen, And as we discussed previously, that radiation was at first dominant, and nowadays it's like a very minimum percentage of the composition of the cosmic inventory.
Yeah.
I was wondering if, like, this could be a problem of a phase transition. Like, for example, maybe, I don't know, like, matter in the universe pass through some extremely rare quantum field like processes that makes them, for example, have to lower their nucleation. So then maybe it's just a matter of phase transition problems and not really just another thing.
Okay, good. Let me talk about phase transition for a moment. So there's, of course, theoretically expected or known phase transitions, like the electroweak phase transition that we knew happened. And in fact, it will also change what's radiation, what's matter, because it gives masses to particles. So initially, everything was radiation because the Higgs mechanism hasn't taken place, and everything is kind of massless. And then you have to wait until the electroweak phase transition in order to separate matter and radiation. There's also the QCD phase transition, which kind of absorbs quarks into hadrons, and the pions in particular, mostly. That also changes kind of the balance of things, or the number of relativistic degrees of freedom changes sharply at the QCD phase transition. So those are two phase transitions that we know are there. We even have observational evidence for them from cosmology. I think what you're asking is something more speculative. Could there have been extra phase transition before? Okay? And it's hard to tell often because the hot Big Bang or thermal equilibrium is a very good erasure of that information. Thermal equilibrium just will make things, depend only on density and temperature and very kind of coarse-grained parameters, and it's hard to tell what happened before. Yeah? As soon as things come into thermal equilibrium, they're described by just the average properties of the fluid. And so it's, I think, hard to tell whether there was something before, but people are always imagining that maybe gravitational wave, depending on the nature of the phase transition, whether it's first order or second order. If it's first order, there can be violent bubble collisions that then produce gravitational waves, and you can maybe look for those, and those are not washed out by thermal equilibrium and so forth. Okay.
But is like any work on that? Like, for example, I don't know, trying to combine different fields in order to like search deeper into a phase transition thing?
Yeah, there's definitely plenty of work. Maybe we discuss afterwards. There's definitely people trying to use, in particular because there's no other way of probing these type of things. You need to use cosmology or astrophysical observations to see those type of things. And so people are very interested, I think, to try to look further back in time. A collider gets you to the electroweak phase transition, but not much further. But cosmology, in principle, can get you further to even higher energies and more speculative physics.
Thanks.
Okay. Yeah.
I believe in March this year it was found that the universe expands in not every direction but the same speed. I think they call it Hubble tension. Does that relate to what you have told us, or is that any problems?
Let me comment. There's two different things. You actually said one thing and then you said Hubble tension, which you said something about the universe not expanding in the same in all directions, which would be a violation of isotropy of the universe. Once in a while this is found, and I'm not so convinced that this is very solid. Let me maybe use this as an excuse to talk about the Hubble tension, because it's something else. Okay. So the Hubble tension is a tension between this measurement of the Hubble parameter h0. So I gave you a value which was 68 plus or minus 2, which already revealed my bias towards the Hubble tension, because there's actually a second value of 72 plus or minus something of order 2, which is at 5 sigma inconsistent with this value that I quoted. Yeah? And so it turns out there's actually two different ways. One way is called the local or late time way of measuring the Hubble constant, which is actually the one that Hubble used by measuring the distances to galaxies and their velocities and fitting a curve that gives us the expansion rate today. That's done with the supernova explosion plot that I showed you, and actually it gives you a larger value than the one I quoted. The value that I quoted is an independent second measurement, which uses measurements of the cosmic microwave background and then a model of the cosmological a model using all these components that I just discussed to predict from early time measurements of the cosmic microwave background what the Hubble constant should be today. And those two things don't match up. Okay? So it could be that one of the two measurements is incorrect. That's the simplest explanation. Or it could be that cosmological model is incorrect and that this indirect measurement that I was quoting needs to be adjusted by some extra physics that then makes these things line up. Because one thing is effectively measuring just early time measurements and then predicting the future, and the other one is measuring the future directly, and those two things don't match. That's the Hubble tension. Okay? That is, I think, more serious than the anisotropy. This anisotropy comes every few years and goes away. Yeah. All right. Okay. 5-10 minutes. Okay. Okay, I'll use 5 minutes just to start, and maybe in the beginning of next lecture I will review this quickly again. So now that we discussed that the universe is expanding, and we also even derived how it is expanding, we have the main equation to describe it, and how densities evolve when the universe is expanding. We can go back in time and discuss a little bit the early universe and the hot Big Bang, okay? Because if the universe is expanding, it means at earlier times, things were closer together. In thermodynamics, when things are closer together, they speed up. So the universe is hot and dense at early times, okay? And as we also saw, that it's mostly dominated by radiation. So there was a bath of essentially massless particles that were kind of interacting with each other via kind of mostly electromagnetism. Charged particles were kind of colliding with each other. And so that's the initial state of the universe, okay? It has an average temperature, because if I average over all of space, the average kinetic energy of these particles is a temperature. And then as the universe expands, because it's radiation, energy goes down as 1 over the scale factor, and temperature also goes down for the same reason as 1 over the scale factor. Yeah? So the temperature will decrease as the universe expands by exactly 1 power of the scale factor, for exactly the same reason as the energy just stretching by the wavelengths of the particles stretching by the scale factor. So then we can ask, if we start at very high temperatures, what will happen as we go forward in time? Okay? And as we will see now, I'm just going to sketch through a couple of milestones in the history of the universe, and interesting things happen at different events. And in fact, things happen on a logarithmic timescale. So there will be a lot of interesting things happen in a split second, and then for a long time, nothing. Okay? And then us. Okay? The next interesting thing. But it's really, you have to think in cosmology in logarithmic timescales. And things are bunched up at early times, and very much nothing, and then us. Okay? Okay, so let's start, in fact, at a time of roughly 10 to the minus 19 seconds after some moment that we call the first moment when the universe was in thermal equilibrium, the hot Big Bang. This is a bit of an arbitrary kind of scale. So at that moment, the universe was filled with almost equal amounts of matter and antimatter. Okay, so I've indicated this here in red and in green. There's matter in red and antimatter in green. Okay? But it turned out that there was, for every 10,000, more, 10 to the 10. For every 10 to the 10 antimatter particles, there was 1 extra matter particle. And that was necessary because when you put matter and antimatter together, of course, they annihilate into radiation. And if they had equal amounts, of course, it would just be pure radiation. And that's a pretty boring universe. So what happened instead is that there was 1 matter particle left for every 10 to the 10 antimatter particle when they annihilated. And so why that happened, we don't exactly know. Okay? There's many theories of so-called baryogenesis that explain this asymmetry between matter and antimatter. But as of yet, no good observational test of distinguishing these different possibilities. But of course, it's crucial. Without this asymmetry, we wouldn't be here to discuss it. Okay? So it's extremely important that some mysterious event happened at around this time. Next, I'm going to jump forward to the time 10 to the minus 5 seconds. This is the moment of the QCD phase transition that I mentioned already in passing. Yeah. So it's about 10 microseconds. At 10 microseconds before that time, the universe was so hot and energetic that individual quarks and gluons were kind of separate particles in the plasma. QCD was asymptotically free at those energy scales. But then as the universe expanded and cooled, you reach the QCD phase transition, and kind of these quarks combine into protons and neutrons, and also pions as hadrons and mesons. Okay? And so from that moment on, kind of individual quarks cannot be seen anymore as free particles. The next interesting moment, at least to me, is 1 second after the Big Bang. This is the moment when kind of the expansion of the universe had cooled enough for the weak scale interactions to become ineffective to keep neutrinos inside of the thermal bath. Okay? So the strength of the weak interaction depends on temperature, actually to the 5th power. So it actually depends pretty sensitively to the temperature of the universe. As the universe expands and cools, the weak force will get weaker and weaker, and at some point it deserves its name. Yeah, at early times actually it wasn't weak. Okay? But then as the universe expands, it becomes weak enough for neutrinos to decouple from the thermal bath. And so the neutrinos, if this is the thermal bath of protons and neutrons, and then we have also electrons, which I haven't plotted here, then at this moment in time, 1 second after the Big Bang, the neutrinos will start free streaming. Okay? And so we can actually discuss, it's very interesting to discuss whether we can see this effect of this cosmic neutrino background. In fact, those neutrinos are still streaming through this room right now. They're just extremely low energy neutrinos that we can't observe with terrestrial detectors. But at early times, those neutrinos were still radiation. They were 40% of the energy density of the universe. So they affected, for example, the cosmic microwave background photons. So we can actually see the effect of those neutrinos in the sky when we look at the photons from the early universe. Okay? So then the next important event is 3 minutes later. At 3 minutes, kind of protons and neutrons combined into heavier elements. So all of the light elements like helium and up to lithium were produced in the hot Big Bang. Okay? That's when it stopped, because then the expansion of the universe kind of made this process inefficient. And heavy nuclei were actually made inside of stars. Yeah? So they were made inside of stars up to iron, and then they needed stellar explosions like supernovas to produce things that are heavier than iron. Okay? But actually all of this can be tested experimentally. That's what's amazing. So you can actually predict, using just the standard cosmological model, you can predict the relative abundances of the light elements. So in particular, you can predict that there's a 1-to-3 ratio between hydrogen and helium. You can then go out and look at gas clouds in the early universe where there was little processing, no star formation yet, that changed these abundances. And when you look at those distant gas clouds and you measure how much hydrogen there is and how much helium there is, you find this 1-to-3 ratio between them. And so it's completely consistent with the fact that they were produced in the Big Bang. Yeah.
Sorry, regarding what we saw in the previous slide, so that means that also the neutrino oscillation gets modified?
Neutrino what? Oscillations?
The oscillation of neutrinos with the previous process?
I wouldn't, why do you say so?
Well, what you explained about the decoupling and the freeze out of neutrinos.
Yeah, but neutrino oscillations is just a free propagation of the neutrinos. So it has nothing to do with kind of the interactions of the neutrinos with kind of the rest of the plasma.
So it doesn't get affected?
I mean, there are still, all the different mass flavors of the neutrinos will have their individual oscillations. We can't see it because we have no probe at 1 second after the Big Bang to kind of probe those neutrino oscillations, but there's no reason to suspect that that they're not there.
Okay,
yeah.
okay.
Okay, I should wrap up. Actually, there's only 2 more events that I want to mention, so maybe if I can just mention those, then I can stop at the right place. So then the next and a really important event is then there's quite a gap. So we were at 3 minutes when the light elements were formed. Then 370,000 years after the Big Bang is the first moment when the temperature had dropped below the ionization temperature of hydrogen atoms. Okay? Before that, the temperature was higher than the ionization temperature, so you couldn't form neutral atoms. Because if you tried to do that, things would collide at such violent energies that it would rip apart the atoms. But then at this particular moment in time, they call it the moment of recombination, that's when the universe had dropped in temperature enough for the first stable atoms to form. That's an important event because when atoms weren't stable, but the universe was made out of a plasma of charged particles, light can't travel through a plasma of charged particles because light interacts with charges. Okay? So at early times, the universe is very dense and it's a plasma, and the light can't travel very far. In fact, the average light travel distance was the size of an atom, roughly, at this moment in time. But then at some very moment, there's a sharp transition at recombination where the mean free path of the photon becomes infinitely large. They just start free streaming, just like the neutrinos were free streaming. And so those free streaming photons is what makes up the cosmic microwave background. So this is still radiation from everywhere around us coming from this moment when the universe first became transparent to light and the first stable atoms were forming. And it's really incredible that we can see this. Yeah, it's the afterglow of the Big Bang. Undergrad students can now measure this. This used to be a hard measurement and surprising measurement, and this is actually a measurement of the curve of the cosmic microwave background made by Kobe. The data points are actually the accuracy of the data points in this intensity versus frequency plot. So it's a perfect black body spectrum, which tells you that it's coming from something thermal equilibrium all around us. Actually, the accuracy of the data is so large, it's so good that I couldn't draw error bars here because the error bars are smaller than the width of the line that describes this black body spectrum. So it's the best black body ever discovered in nature or the lab. It's better than anything you could make in a lab. And here I've plotted residuals so you can actually see how good this measurement is. Okay? So you can measure actually this black body curve. The peak of the black body curve tells you the average temperature of the universe today. It's 2.7 to 3.5 degrees Kelvin. You can convert that now into a density. That's how we know the density of photons in the universe. Density of photons is 410 photons per cubic centimeter. So, okay, 5 protons per cubic meter, but 410, so many more photons than protons. Yeah? That's actually related to this factor of 1 in 10 to the 10 baryon asymmetry. That's related to the fact that we have 400 photons per cubic centimeter, but we have 5 protons for a much larger volume. And the temperature is so low, so we actually measure this in microwaves. That's what we call it, the cosmic microwave background. Okay, last event. So 1 billion years after the Big Bang, matter collapsed into stars, galaxies, and so on. And in the next lecture, in fact, I will discuss that process in more detail. How small fluctuations, in fact, that we can see in the cosmic microwave background grow into stars and galaxies at late times. I'll stop now.
Should we take one question, or is that... Yeah, okay, you already had before, so let's take one question, and then we're over time.
Hi, thank you for your lecture. I was curious about the formation of light nuclei that you mentioned.
Yeah.
So in experiments that actually produce quark-gluon plasma in laboratory, the production of light nuclei is either considered to happen inside of the QGP or after the thermalization. And there are two different models, the coalescence and the thermal model, that describe these two kind of processes. I was wondering if in cosmology there are different these two models are also considered as well, and if there are any consequences of choosing one model over the other.
Okay, yeah. Well, I don't know, but you should tell me. So not to my knowledge, I have never heard of any of this being relevant. So short answer is I don't know. But if you tell me more about it, I can check it out.
Yeah, so. Okay, I mean, it's nice to have the questions during the talk, so let's thank Daniel again and continue tomorrow.